Hello, this video will show you how to set up the Wishbone camera controller for an OV5640 camera from OmniVision with the NEORV32. We are using the WaveShare breakout board for the OV5640, specifically revision board C. So I highly recommend that you go back and watch the 3 setup videos for the new RV32 plus NPU system, because a lot of concepts will overlap from those videos. So let's go ahead and create a new project. So just copy paste like before, rename it to camera. Terminal. Go ahead and open the new project. So last time for the NPU system we just had one clock, which was which is just it generated a 72 megahertz clock from 12 megahertz clock. Now for this design, like for the current system, we want to run the new RV32 at 72 megahertz, and we want to run the camera controller at 24 megahertz. Specifically, not specifically exactly the camera controller per se. It's like the camera's XCLK, the external clock reference, requires 24 megahertz for clock speed. At least that's the recommended speed. So go ahead and delete the old NPU files because we don't need them, and we'll delete the old PLL block files as well. So just remove them. Removed. We'll go back to this is the repository for the camera controller, again linked in the description. So we'll just go ahead and download this zip file. Extract. So yeah, firstly you're like interested in the VHD files, so go ahead and import those. This input files, add existing file. So once we have this file, so there are a few major changes that we'll have to make. First, we'll need to modify the constraints file. So right now, I just FPGA only works with the onboard LEDs and the UART pins, but we also but we want to of course connect the camera's interface to the FPGA, and which will be passed to the new RV32. So we'll need to update the constraints file. So the folder already has a constraint file in there. The setup file is the constraints file. Just Control C and paste it. Okay, that's not good. Of course, we need to open it. So we have the constraints file ready. Now we'll need to make 2 more changes. First, we'll need to update the top level file. This is the ECP5 top level file with the PLL block, and then we'll also need to like change modify the ports we are exposing, and we'll also need to modify the template files. Right now we are instantiating the NPU, so now we'll need to instantiate the camera. So first let's modify the ECP5 top level file. So I'll copy it over from the existing source. Of course, these files will be linked in the description. So I've copied over the the modified top level file. So as you can see, the camera interface has been exposed. So we have the SIOC and SIOD pins, which are used to program the camera's onboard registers, the camera's VSync and HREF signals, the PCLK to coordinate pixel capture logic. XCLK is the 24 mega is what we have to like supply the 24 megahertz clock to. Data ports from the camera's reset pins and the camera power down pins. Okay. Again, we are not going to go in depth of how the camera peripheral is designed. We're just going to focus on how to get it working with the setup. So it's NEORV32 plus camera controller. So for convenience sake and to like show you in real time, the LED pins have been so the ECP5 onboard LEDs now show the data output from the camera, so you can see, okay, is the camera streaming data or not. So it gives you a quick way to verify what's going on. Otherwise, we'll also modify the camera interface for the NEORV32 template file shortly. For that, we'll now work on creating this module for the this PLL block. Sorry. So go ahead and run Lattice designer again. Design location, design name. Let's call it PLL 122472. Like before. Just to show it's different, I'll just add a module as well. Remember to set it as VHDL. Create designer. PLL block opens up. PLL 12. Okay, I forgot to. Okay, doesn't matter. 72 inst. So again, our input clock speed or clock is 12 megahertz from the onboard oscillator. Can enable high bandwidth feedback mode. Primary clock output, we want 72 megahertz from here. So because we want to run the system at 72 megahertz, and we'll enable clock. So this the first CLK OS, this will be 24 megahertz and will be fed into the OV5640's XCLK pin. Again, we want 0% tolerance because yeah, and yeah, PLL lock is sticky. Go back to frequency, calculate, it goes through, configure, no errors, close. It's running. Yeah, generate, design loaded. So now we have the design here. So what we can do is like before, we can go add existing file, PLL 2472 module. We want the VHD file. Yep, now we have it in the design. Going back to the this is the top level file. I'll just quickly make it exactly how it's supposed to be. So the module is now configured, so PLL block has been instantiated. Now, this is the input system clock as before, 12 megahertz. This is the 72 megahertz clock speed for the system, NEORV32, and in the future the NP as well. This is the XCLK. This is the internal signal, and this is fed to the output XCLK, which is like the physical pin on the FPGA, which is connected to the camera. And again, we have the locked signal, which is used to coordinate the reset. In the constraints file, as you may see, an interesting thing is that this is, it's not. Yeah, I don't. Yeah, we are using the primary net constraint here. So please remember that when you are trying to use a system generated clock for an external device. Alright, so we'll now modify the minimal boot template file. So previously what we did was we instantiated the NPU. We don't want it now, so there's no control slash, so I'll quickly comment it out. Okay, so first we'll for the NEORV32 top level file, we'll expose the camera interface so we can pass it to the camera controller. So in essence, we are like, okay, physical pins from the FPGA are passed to the NEORV32 top level file, which are then passed to the camera controller. Then we again need to declare a component for the OV5640, and then we instantiate it. Now one thing, you may get this error, is that in project in active strategy simplify pro settings, you should enable VHDL 2008. So we should use VHDL 2008, otherwise the Wishbone camera controller won't work. Right. So now that this is done, see, as we can see, we have 0 errors. So now we can start generating the bit stream. Oh, it failed. Okay. So the error was when we were adding the PLL block via input files, we had set the copy existing file to directory option, and therefore it threw an error. That was it. Right, so now it's generating the bitstream. So the bitstream generated, so we can now program the FPGA. You can also send the hierarchy. OV40 is under the NEORV32, which is under the main ECP 5E and top level file. Just select the correct bit stream. And program it. Yeah, I forgot to. Take it on, program it. Once you've programmed it, the camera will make a click sometimes. It just says it's been programmed. As you can see, 128 by 128K from before. Camera's there. Thank you. We'll look into running ADA programs on it later. Thank you. Once you've programmed it, the camera will make a click sometimes. It just says it's been programmed. So you can see the data, there's activity on the camera's data pins, and therefore the LEDs are blinking very quickly. So if I just place my hand in front of the camera, you'll see the there's a quick check to verify, okay, your camera is streaming or not.